Welcome to the Grandmaster series. I'm your host, Jay, and in this episode, we'll delve into the intriguing world of building robust recommendation systems, featuring the winning solution from the prestigious Amazon KDT Cup 2023 competition. I'm incredibly excited about our discussion today as we will be engaging with some of the world's leading experts in data science who were part of the victorious NVIDIA Merlin team. Together, we will analyze their approach to the challenge, gaining valuable insights into the development of a top tier recommender system. Before we dive in, I'd like to mention a couple of things. Any material or resources related to today's discussion will be linked in the description below for your convenience. And don't forget to subscribe to our channel to stay in the loop for upcoming videos in the Grandmaster series. Now, without a further ado, allow me to introduce our esteemed panel. First off, we have Benedict, a deep learning engineer at NVIDIA working on recommender system. He holds a MS in data science from Columbia University and previously worked as a data science consultant at McKinsey. Next, we have Chris, a senior data scientist at NVIDIA. Chris has a PhD in mathematics and computational science, and he's a four-time Kaggle Grandmaster. Next, we have Gilberto, better known as Jiba, a senior data scientist at NVIDIA. And prior to this role, he worked at various companies, including Petrobras, Airbnb, and Siemens. Jiba has held number one position on Kaggle for more than 2 years. Next, we have John Francois, a three-time Kaggle Grandmaster and a distinguished engineer at NVIDIA. He holds a PhD in machine learning and has published over 70 scientific papers in peer-reviewed conferences and journals. And finally, we have Kazuki, a senior data scientist at NVIDIA. He's been a Kaggle competition grandmaster since 2019, and he has had six top two competition rankings. In this episode, Chris will kick us off and provide a bit of a background on the competition. Now that the stage is set, I'd like to hand it over to Chris, and I'll be back at the end for the Q&A session. Chris, over to you.
Thanks, Jay. We got a fantastic Grandmaster Series episode today. 4 Kaggle Grandmasters of NVIDIA depicted here, and one NVIDIA Recommender Systems expert teamed up recently and competed in the KDD Cup competition. We worked really hard for 3 months. We built dozens of innovative models, and we achieved amazing results. Today, we're going to share our work with you. In today's episode, first we will introduce the KDD Cup 2023 competition. The competition was 3 tasks, and our solution had 2 stages. First, we'll talk about task 1 and 2 and our stage 1 portion of the solution. Next, we'll talk about task 1 and 2's stage 2 portion. Then we'll talk about our task 3 solution, and then we'll have questions and answers. The KDD Cup competition is a prestigious annual competition associated with the KDD, that's Knowledge, Discovery, and Data Mining Conference. They've been doing it for 29 years. This year, they teamed up with Amazon to create a session-based recommender system challenge. In this challenge, teams have to build models which take user session as input. That's all the products that a user has engaged with, and then the model needs to predict the next product that they're going to engage with. There was actually 3 competitions in one called tasks. And in the first task, the user sessions are in the languages of English, German, and Japanese, and we have to predict the next item. For this task, we have lots of training data. Task 2, the user sessions are in Spanish, French, and Italian, and we have to predict the next item. This is more difficult because we only have 1/10 of the training data. To be successful in this task, you have to use transfer learning. Your models need to learn patterns from the popular languages and then transfer that to the underrepresented languages. Task 3 was different. In task 3, instead of predicting product IDs, we need to predict the next product title. And what makes it really difficult is many of the titles don't even exist in the trained data. So this is a generative AI text challenge where participants need to use large language models. The diagram here shows the task. So shown here is one example test user session. And we can see in blue that this test user interacted with 7 items in this session. Now, let me point out, in today's presentation, we're going to use the word item and product interchangeably, the same thing. And then you see, once we have their session, our task is to predict the next item they interact with. Our models are given trained data from the past, and they need to predict test data in the future. The trained data has 3.6 million unique user sessions. Now, I'll point out that some of the sessions can be from the same user, but we don't know this because the data did not give us any information about users. All we have are user sessions, which are sequences of items. Furthermore, they didn't give us any timestamps. So we don't know when they occurred, but they are in the correct order. The trained data has a total of 1.4 million unique items, which are products. And some items exist in the multiple languages, and some items, exist in a few, and maybe some items exist only in one language. For each item, we're given 11 properties. For example, the title, brand, color, price, etc. The metric for task 1 and 2 is MRR at 100. This is mean reciprocal rank. What this means is, for each user session, we predict 100 items, and we order them from most likely to be the next item to the least likely. And the way it's scored for each user, if each user has one correct only one correct answer, one next item. If we get it correct on our first guess, then we get a score of 1 for that user. If we get it correct on the second guess, we get a score of 1 over 2.5. Third guess, 1 over 3, etc. Nth guess, 1 over n. And then our models need to make predictions for thousands of test user sessions. And then our final score is the average of all these individual MRRs at 100. Task 3 has a different metric, because if you remember, in task 3, we're predicting a title, which is words. So the metric is blue, which quantifies how similar our text is to the actual text. And we'll talk more about this metric when we discuss our task 3 solution later. Shown here are the results of the KDD Cup competition. So over 450 teams competed, and shown here are just the top 3 teams. So your final score overall is the sum of your rank in each of the 3 competitions. And so lower score is better, and the best score you can get is 3. And you can see Team NVIDIA Merlin here at the top. We actually were able to achieve first place in each of the competitions. We're so excited. Our models were truly amazing. And today, we're happy to share these models with you. So first off, we have Kazuki, who will begin presenting our solution.
Thanks, Chris. In this slide, I will present two-stage recommender system pipeline. In recommender system, it basically consists of 2 stages. First is candidate generation. This retrieves item candidates from all items using user history. Second stage is ranking. This re-ranks the candidates we obtained from first stage candidates. Okay, please move on to the next slide. The previous slide explains a high-level idea of the two-stage recommender system, but this is the detailed view of our solutions. First, as you can see, we have many different stage 1 models for candidate generation. The boxes represents only type of algorithm. Actually, each box can be multiple pipeline with different parameters. For example, we use the Co-Visitation matrix, which was introduced in OTTO solutions. We also use BERT text embedding similarity and text similarity scores. We will explain these parts later. Moreover, we use neural net approaches. In stage 2, we ensemble those candidate score because we need to eliminate candidates that we don't use. Without using this, we we have a lot of candidates to calculate and it may take ages. Next step is feature engineering. We use session features. For instance, how many items does this session have? And the candidate feature is item meta feature. We have, for example, item brand, color, and size. And next is Co-Visitation item features. And this is the feature from Co-Visitation matrix. We have item meta feature unlike OTTO, so we can generate a lot of Co-Visitation matrices using it. For instance, using a brand, we can find a similar brand, and using color, we can find a similar color. And then we input these features into GBDT and ensemble those GBTs as well. Okay, Jiba will explain BART embedding in next slide.
Okay, thanks, Kazuki. So I start to describe some approaches used to build features in our models. So the idea here is to use transfer learning to generate that features for the Reranker models. So we use some pre-trained large language models to input item properties and extract a vector representation of each product, right? This is the main idea. One advantage here is that no training step is required, as you just run inference using already pre-trained language models. So basically, what we did can be summarized in these three steps in these slides. First, we concatenate all given item information and build a large sentence containing all data of each item. For example, like the item title, country, price, color, model description, everything described an item into a sentence. Then we feed this sentence for all the items in the dataset to the pre-trained language models, and we store the outputs of the last layer in a table of vector embeddings. Each of these vector embeddings is a mathematical representation of each item. And finally, we have a table of more than 1.5 million item vectors, and the size of each vector ranges from 512 to 1024, right? Depending on the language model is selected to extract that embeddings. Then for each session, we take the last item, let's say item 2 in this example, then we pick the vector embedding of this item 2 and compare it with all other 1.5 million vectors in the table to retrieve the top 100 most similar items to item 2. The method used here to calculate the distance to each vector, it was the cosinus similarity. And it was chosen especially because it performed better for the competition metric. Now, for the single session, we have a new table with 100 item candidates and the similarity score of each candidate in this table with item 2. And this information can be used as features to train further Reranker models. Next slide, please. So following the previous slide strategy to generate features, we tried several language models, but finally select only 5 language models to extract embeddings for product items. The features actually generated by this method can be considered unsupervised and doesn't need any cross-validation strategies in order to calculate the metrics when applied to the train set, right? You are just running inference in the language models. So given the 5 item embedding tables for each one of the 6 locations present in the dataset, we ran a nearest neighbor search algorithm with cosine similarity metric to find the top 100 most similar items sorted by the similarity score. So given each language model we selected, we provide a list of 100 most similar items, and we use the last item in the session as the pivot item to generate the candidates for each session, right? Given the candidates generated, we calculate the competition metric for each combination of language and region as shown in this table. As you can see, each language model provides different performance for different language, but in average, the performances are very similar with a small standard deviation. An anomaly can see in Alien AI Spectre model, specifically for the Japanese language that scored worse than the other language models. But all the 5 language models here are multilingual, so probably Alien AI Spectre is just not efficient for Japanese language in this unsupervised approach. Okay, then I can combine all the 5 language model vector embeddings side by side in the new table and run again the same nearest neighbor search algorithm. Doing that, it scored 0.209 in task 1 local validation and 0.261 for task 2 local validation, right? And the leaderboard score showed a good correlation, confirming this method works. Okay, next, Jean-Francois is going to talk about how to make item embeddings now in a supervised fashion. Jean-Francois?
You're on mute.
Sorry, Shiba has presented the use of pre-trained model as is, but we can fine-tune the embeddings possibly, and here is one way. So we devised a model that takes as input the session embedding, the embeddings of the session items, and compute an embedding for the session embedding that you see there. So instead of picking one item and its embedding, we have a model that computes an embedding for the session from the item embeddings. Once this model is trained, we can also extract its embedding table and from there use product embeddings. That's what we see at the top. And the rest is same as for JIPA. For a given session embedding, we look for the nearest neighbor product embeddings, item embeddings, and we retrieve the top 100. So I will show the model in next slide, but an improvement was to not start from scratch and start from the same embedding that JIBA used, which is to use a pre-trained. Here I tried several. Best one was XLM Roberta, trained on sentence pairs. So that's one of the best model. And fine-tuning the embeddings improve the quality, the competition metric on the retrieved items. So on the bottom right, you see a graph that evaluates various candidate generation methods, including the one JIBA presented, including co-visitation matrices. And these are cross-validation scores, but the leaderboard scores show the same. The fine-tuned embeddings are significantly better. They are not good enough to win the competition, but they are a good feature for on stage. Next slide, please. So let's look now on the model, which is actually quite simple. Here I take a session with 4 items, 3 prev items, and 1 next item, and I want to train from it. So the model first retrieves embedding for all items. And then it applies a convolutional layer. You could think of it as a linear layer at this point, that just combine the private items embeddings into one embedding. And then the loss function is to maximize the cosine similarity between the session embedding, the output of the convolution layer, and the next item embedding. If we just do that, we will converge all embeddings to the same. So we need also to have some negative, some minimization. So for this, we randomly select a large number of items. I use 4,000. And for each of these random items, we want to minimize its similarity with the session embedding. So basically, we want the session embedding to be as close as possible to the next item embedding and dissimilar to all the other ones. That was a base model, and then we can just move the pattern to the left. So instead of predicting the next item embedding, we can predict the last private item embedding, so one here, from the previous three. So we just slide the convolution layer by one, and that's why it's a convolution layer. And actually, in practice, we took the last 16 items of every session. We pad if the session is smaller, and then we apply a convolution layer, which will compute 14 embeddings. And then each of these embedding its similarity to the next item embedding is maximized. And this concludes, so this is really a simple model, which was surprisingly efficient. Maybe it's only working on this data set, but it's working there. With this, we'll let Benny present another way to learn embeddings.
Thanks. So Jean-François explained the method to use convolution layer as processing the input sequence. Another method is, instead of using convolutional layer, I use a transformer layer, which is like a transformer block. So you have the input sequence of items. Use the transformer layer inspired by large language models. And then you have a session representation, it's a hidden representation. And then you can calculate dot products or different methods to calculate the final probability scores and use the loss functions. What is special in this model or type is we use multiple inputs, not only the item ID, the item features brand, color, and so on, including bird text embeddings, and feeding it through a one-layer MLP. Another thing is about the masking. It's from language model training as well. Masking is how to drop out the items, which is the target. And this is MLM, randomly masking any item of the sequence. So it could be in the middle of the sequence, and then you have the context before and after to trying to predict it. And this is another strategy or add some kind of diversity. Another way, Jean-François already mentioned, you need negative samples. In this model, we used a mix between uniform sampling and in-batch sampling. The advantage of in-batch sampling is it has a popularity bias, it's popularity sampling, and the uniform sampling corrects the popularity bias in it. And this combination worked pretty well in this kind of model. Finally, another method here used is to use multitask learning. It's not only trying to predict the next or the masked item, it tries to predict the item features of the masked item. So it tries to predict which brand should be this target item have, or which color, which material. And so there's a lot of different training in total. There are 4 different models trained. One's only using the previous items or previous item with the next item in the trained data set, then the single task and the multitask. And this gave a lot of different diversity. A lot of this functionality is available in our open source library, Transformer for Rec, the masking strategy, the different transformer blocks over 64 different architectures. We used XLNet here, and there's a lot of examples you can try out if you want to experiment with it on your data set. So we talked a lot about the stage 1 models. We're going now forward to the stage 2 models. Yeah, the stage 2 is about how to aggregate it. First, I will provide a summary of it. As Katsuki already mentioned, we had a lot of different stage 1 models, and there were a few boxes, but overall, we had like 60 to 70 individual candidate generation process due to all the different hyperparameters and combinations. And we need to ensemble them using their like a weighted average rank. And just ranking them improved the local CV by 0.01 comparison to like the best models, single models. It's just ensembling and stacking always helps. The feature engineering part is we adding the raw score of the stage 1 process, which is a kind of stacking, because then the boosted tree can use it as an input. We add popularity of the items as previous item or next item. We use like session lengths and the locality, like which language it was. The probability of the item feature, like if the candidate has a certain brand, what is a certain model predicting is the likelihood that this brand is correct. Same like we can do co-visitation metrics on item features. This gives all like 150 features around, which we can use for training. Finally, we use for re-ranking cut boost or XGBoost model with Dask, with like different loss functions to have diversity again for ensembling later. Like we have once a pair logic, pairwise loss, and then a binary loss. And this is like giving our final scores. Going further. One challenge is about the distributed training. So as I mentioned, we had like 150 features. And if we have 100 candidates per user, we have like 360 million rows. So this is a really, really large data set. How did we scale it? Is like XGBoost supports Dask, which is a library to distribute Python workloads. And it supports with Dask QDF to run this on GPU as well, with XGBoost on GPU. So we used 8 V100 GPUs, each is 32 gigabyte of memory, to get to a 256 gigabyte of GPU memory. And we saw like, if we train it over the whole data set, we saw like an additional boost on the leaderboard. And this was like the advantage of like scaling it. It's like took a lot of time running it just normally. With 8 GPUs, it was still like half an hour for one training run. And in addition, scaling it to this large data set was not trivial. It required like some special libraries for it. And this was able then to like train on the full data set. So Chris will continue to provide some details about the stage 2 models.
Great, thanks, Benny. So I liked this diagram here. I think this diagram here is a nice illustration of both stage 1 and stage 2. So if you remember stage 1, for each user session, we're finding a bunch of candidates. And then Benny just talked about stage 2, which is where we essentially are going to train another model, gradient boosted trees, to figure out what are the best candidates for each user. So let's imagine that we decide to have 100 candidates per user from stage 1. What we do is we create a data frame shown here, and then for each user session, we'll have 100 rows. Each row will have one of the candidates, and then there'll be a column for the user session. And then, of course, we'll add a target of zeros and ones. We'll put a 1, whichever item is the true next item, and a 0 otherwise. And we're gonna train a Reranker model. But of course, to train a model, you need columns of features. So a lot of the work in stage 2 is coming out with features. So here is 4 features we're particularly proud of. They showed up in our top 10 feature importance. But what they are is we trained a recurrent neural network to predict the brand for each user session. And then we can then use it in the data frame to actually make a column. So for each candidate item, we can predict what is the probability that that candidate item has the correct brand for the associated user session. We could similarly do this for color, size, and model. The model architecture looks like this. So when we train the model, our training data is a bunch of user sessions, which of course is a sequence of product IDs. And for each product ID, we have various properties. Specifically, we have brand, color, size, model. So we input the user session into the model, and then there's an embedding layer which converts these 4 properties individually into an embedding of length 768. And then each item will have 4 embeddings. We add those together. Now each item is represented by 1 vector of length 768. So we have a new sequence of these vectors shown here in the middle, those little teeny squares. And then we put this new sequence into a GRU with 1 hidden layer of size 768. And then the model has 4 heads. So one of the outputs coming out of the GRU, it does a dense, for the predicting brand, we go into a dense layer of 768, and then we go into another dense layer, which is its size is the number of unique brands, and we use a softmax loss, and that predicts brand. And similarly, we have a model head, which predicts the color, the size, and the model. And I'll point out that a good way to predict actually what brand a user is going to buy is you can actually look at the user's last item in their session. And if you use the brand of their last item to predict their next item, that actually does pretty well. Maybe it's 40% of the time correct. But what's exciting is this GRU model shown here, it actually beats that baseline in all 4 predictions. So it'll exceed that simple baseline and brand, color, size, and model. So truly, the model is using information from the entire session. It's looking at the behavior of the user, how often maybe, and then it actually predicts these 4 properties. All right, so to be successful in task 2 and actually benefit in the whole thing is you want to use transfer learning. So we use the transfer learning in many different ways, but one way to use transfer learning is to sort of translate a user session from one language to another. So some product IDs exist. It's the same product ID, but it's actually exists in multiple language. So the top row shown here is a German user session. We can see that they have 4 items in their history, and then it shows their next item. And it turns out that amongst these 5 product IDs, 4 of them also exist in Spanish. So you can see we could take this German user session and actually translate it into sort of a Spanish user session. There'll be 1 item missing. You see that says does not exist here. But nonetheless, we can input this data into our models to help train. So, for example, in the last slide, we saw the GRU, which predicted the 4 properties. So specifically, when we were training a GRU to predict the color for Spanish users, this picture here shows how we can actually use many of the German users, translate their session into Spanish, and then use the sequence of Spanish colors use the whole user session sequence to then train and predict the Spanish color. So this was really effective. It boosted both our local validation and leaderboard score. And that's just one example of many of using transfer learning for stage 2 feature generation. I'll also point out that this idea worked very effectively in stage 1 also. So, a bunch of candidates came from co-visitation matrices. And the way they work is you use a user session and then you compute statistics on how often items are seen together. So if you're creating a co-visitation matrix to help predict candidates for Spanish user sessions, the train data only has 1/10 as many of those sessions as other popular languages. But what we can do is we can take a lot of the popular languages, use this idea of translating it into Spanish user sessions, and then we could use those sessions to compute statistics and help with the co-visitation matrices. And that boosted that using that idea of transfer learning boosted the generation. Just to point out one more example, earlier you saw slides of a CNN model which was trained to learn user embeddings. And if you remember, inside when the items were coming in and it had an item embedding table, well, that model, you can pre-initialize the item embeddings with embeddings directly from a multilingual large language model. So that by doing that pre-initialization, you actually gain information from multiple languages. That's that's a third example of transfer learning. And there's many more. We use, a dozen ways and greatly improved task 2, and it helped a lot using transfer learning even in tasks 1 and 3 also. All right, next we're going to share with you our task 3 solution, and Jiba is going to begin describing it.
Okay, thanks, Chris. Okay, task 3 is very different from the previous two tasks. Basically, task 3 is to predict the next item title based on the user search history. Okay, so like the other two tasks, the last any items seen in a session are given. So basically, it's the same. You just need to predict the title. And we found that in the data sets that there are at least two items in each session. So the thing is, by using the title of the last item seen in a session as the predicted title, scored high in both local validation and in the leaderboard. And we start from this baseline. This happens because some item titles are very similar. For example, title changes a few words from each other related to properties like color, size, or some item-specific characteristics. And many times, the title of the last seen item in a session is very similar to the title of the purchased item. It changes just a few words. For example, if the item is medium or large or the color. So given the leaderboard scores, we estimated it happens for about 1/3 of the sessions in the test set. That's why using less title as the prediction is so efficient here. Of course, the metric chosen for the competition helps with it. And the metric is the blue score. This metric is often used for machine translation models to check the consistency of the translated sentence. And the blue score consists of calculating the precision scores of word grants, specifically 1 gram, 2 gram, 3 gram, and 4 gram, and then taking the geometric average of these 4 precision grant scores, okay? Also, the blue score have a term called brevity penalty, BP, that degrades the metric only if the predicted title is shorter than the ground truth title. The penalty forces the predictions to be at least the same length as the ground truth in number of words. Not Not that also the geometric average method have the multiplication terms, right? So if any of the n-gram precision score is 0, then it zeroes all the metric. So it's very important to have positive precision in all the 4 n-gram scores for this metric. Another interesting fact here is that the hosts provide a test set for task 3 with a different distribution than the train set. And they stated in the competition description that the labels for task 3 test set are from new items not present on the training set. So most of our attempts to correlate local train set cross-validation scores with the leaderboard scores failed. For example, we built generative supervised models that scored blue score close to 0.4, but leaderboard score around 0.2. The only way we found was to correlate the local validation and the leaderboard was by using the title from the last item in the session, in each session, right? And using the last title strategy scored 0.2655 in leaderboard and not for a top 22 place in the competition. Next slide, please. Okay, this is the first model we built for task 3. We have 2 models, and in this first stage, it consists in building a model that selects which title from the last 2 titles seen in the session will be used as the prediction. So basically, we build a binary classifier, right, to pick the title from the last item in the session or the title from the second to last item in the session. It's very simple. And the features used are very important. The features were based in some properties calculated using the combination of the last 2 titles, okay, in the session, and 10 candidate titles generated by 2 supervised modules built for task 1 and 2. So we have a bunch of candidates and the last 2 item titles, and we combine this sentence of the titles, right? And we, based on that combination, we build a bunch of metrics and statistics. For example, we calculate the blue score of the candidates and last titles, the difference in number of words, number of word intersections, number of similar item properties, also like similar color, size, model, material used, and And there's a bunch of around features based just on this approach. All these features are stacked side by side in a table, and we selected the QML random forest algorithm to minimize any potential overfitting effect given the target distribution shift between train and test. To select the prediction title, we use a threshold of 0.4 to select if you're going to use the last title or the second to last title as our prediction. So then we use exactly as is, the title of the last item or the second to last item. This approach boosted our last title baselines by 0.0012. Yes, it seems small, but it's enough to jump to a 13th place in this competition. Okay. Next, Chris will show you our second stage model for this task tree. Chris?
You're on mute, Chris.
Thanks. Yeah, so as Jibba showed, we struggled at first to have an agreement between our local validation and the leaderboard, but eventually we figured out what kind of things improve both the local validation and the leaderboard. And another thing we discovered that improved both was removing the last word on some titles. So if you remember from the definition of the blue metric, it's based off of precisions, not recall. And that's significant because in general, precision means, what percentage of the words you're putting forth are correct. So, if you remove words, it oftentimes increases the precision, and it doesn't matter that it might hurt recall. The only thing we have to avoid is there's this thing called the brevity penalty as part of the blue metric. And what that means is if your title is too short, so we can't just, submit 5 words. And if your title is too short, then you're multiplied by the percentage of essentially you're multiplied by the percentage of your prediction length divided by the actual length. But what we found out was, in general, or what we found out through some submissions is it does appear that the titles in the test data were on average a little bit shorter. So it turns out that we could actually remove a bunch of last words, and we did not get a brevity penalty. Specifically, if we remove the last words from about half, 50% of our predictions, we would get no brevity penalty. So just doing that, just randomly removing, just randomly picking half and removing the last word, that jumped up our leaderboard score pretty good. But to improve upon that idea, we actually trained a large language model, an XLM Roberta base, to choose for us. So the way we did that is we had to create training data which needs a target. So the way we built our training data is we took all of the 3.6 million user sessions that were given to us, and each session has a last item in their history, and they have a next item. So as a pre-processing step, we went through each session and we removed the last word from their last item, and then we computed the blue score with their next item. And then we also computed the blue score without removing the last word, and we compared the two blue scores. And if the blue score increased, then we would give it a target 1, and if it decreased, we would give it a target 0. And so now we have 3.6 million train examples. We have a target of 0s and 1s, and we now trained XLM Roberta base as shown here. Just built a simple global average pooling and had outputted one output binary classification with using a log loss. And then we use this. So we train the model. We use this model to make a prediction on all of the titles that were chosen from the model that Jibba had shown. So we use that model. It tells us which last title to use. We then apply this model, which tells us what's the probability we should remove the last word or not. And then amongst that, we sorted it and picked the top 50% and removed those last words. And when we did this, so I have to say, I guess you already see the answer. You see the slide. You see that it jumped our score up a huge amount. And then it jumped us up in the first place. But I have to tell you, it was quite exciting because, we had trained various models to remove the last word, and it actually and we get a couple submissions each day. And it turns out that this specific one, the Roberta, we trained it for 8 epochs. We did 5 folds on all the data. We actually made this submission on the very last day. So it wasn't until the very last day that we jumped up into first place. And that model, I mean, that's a lot of work to train with millions of samples on this large transformer for all those epochs. So it trained, most of the night. We used dozens of GPUs. And then we sat at our computers the next day and hit submit and said, "Oh, I hope it does well." And it jumped up there. We were so excited. So that concludes our solution. We will now go to some questions and answers.
All right, thank you everyone. That was truly an insightful discussion. I hope our audience found this session as enlightening as I did. Now we are into the Q&A segment of this episode, and our panelists will answer and tell us about building successful recommender system. And the first question that we have is, can you discuss any limitation or challenges faced when using the embeddings in your approach?
I can pick that one, can start. Yeah, we use a lot of embedding approach in this competition, especially based on nearest neighbor search to generate candidates and also features. And running it in 1.5 million item vector is something extremely slow in CPU implementations of the algorithm, make it very challenging to do it in a reasonable amount of time. So we solved it very simple by using QML GPU nearest neighbor that is extremely fast compared with the CPU implementations, right? Yeah, another limitation faces to extract embeddings that can be very slow for large language model. So having access to multiple GPUs can parallelize it and make some huge speed up, and something that will take several days can be ended in coming down in some hours.
Right. Thank you, Jiba, for the answer. The next question is, were there any unexpected findings or results in your solution process?
I'll answer this one. So there were. So the comp was 3 months long. For most of that, the first 2 months, we were actually had the lead in task 1 and 2, and then in the last 2 weeks we had gone to the new test data, and then we were trailing by a little bit, and we just kept trying different ideas, and then we actually made a big discovery, which is we were doing some EDA, and we noticed that there's a bunch of product IDs in the test data that are not present in the trained data. And this got us thinking, how are our models? Are our models doing well? Are they learning these new items? And we also noticed that the popularity of items changed over time. So the test data is in the future, but items that are popular during the time of the trained data, different items are popular in the test data. So we saw this temporal shift, how things change over time. So we ended up taking any of the items that were in the test data, and we actually started boosting their probabilities during when the models made predictions on the likelihood of that being the next item before we picked our final 100 predictions. And it turns out by actually boosting the probabilities of the test items, the popular ones, it actually improved our score a lot. So we were really excited. We found this in the last few weeks, and that helped close the gap, and eventually was one of the contributing factors which helped us take first place in tasks 1 and 2.
All right. Thanks for the answer, Chris. The third question is, what was the most critical factor in improving your model's performance or accuracy, and how did you discover it?
I can answer this. I think it was transfer learning. So we describe it in the video, but the task 2 data was 10 times smaller than the task 1. And so it was hard to train models from scratch, and reusing pre-trained models was useful. For instance, for the CNN, initializing the embeddings with a pre-trained model boosted the score by 0.03, which is really large in this competition. So I would say for the CNN model, that was the most important discovery during the competition.
Yeah, I can add translated learning worked on the boosted tree as well. Like you can train a model per language, or you can train it over all languages, and in the same way, it improved the overall score. The challenge was how to scale these pipelines, as we mentioned in the presentation, how to scale them, because if you add more and more languages to it, the data set gets pretty large. And there's like an engineering challenge how to solve that. And it's not only the training part, all this feature engineering and other processing and combining to scale it always to like the data set. The data set in the beginning sounds small with like 3 million session. I think it's like a few hundred megabytes, but my final data structure had like over like multiple hundreds of gigabytes of intermediate results here and there. So yeah, it gets pretty challenging and fast how big the data set gets.
Thank you, Jean-Francois and Benny. And the final question for the day is, what's the difference between the solution in this competition and the Kaggle auto competition, which was multi-objective recommender system?
I can take this one. One of the big difference is feature engineering part. As I said before, we could use item meta feature unlike OTTO, so we could generate a lot of co-visitation matrices using it. But concept is almost same. Actually, I just copy and paste same code and replace item ID with brand, color, and size. Also, multilingual transfer running is different as Chris explained. And another difference is metric. Auto use recall at 20, but this competition uses MRR at 100. Recall doesn't Recall at 20 does not care about the order within 20, but MRR at 100 does care with 100. So we had to care about low rank items. I think these are the main differences.
Okay, thank you, Kazuki. That was insightful. And thank you to all the panelists for sharing their approach from the competition. Before we wrap up, I'd like to remind everyone to subscribe to our channel to stay updated about our future episodes of the Grandmaster series. You can also find any resources discussed today in the description below. Thank you all for joining us in this episode. We are thrilled to have shared this journey into the world of data science and recommender systems with you. Until next time, keep exploring, keep learning, and remember, with NVIDIA, you are always at the cutting edge of data science.